A computer stores nothing but binary numbers. So how does it store the letter A? The answer is that it does not. It stores a number, and everybody agrees in advance which number means which character. That agreement is a character set, a defined list matching every character to a unique binary code. And the phrase agrees in advance is doing the work, because without a shared agreement, the same number would mean different things on different machines, and text sent from one to another would arrive as nonsense. A character set is a standard, and its value comes entirely from everybody using the same one. ASCII, the American Standard Code for Information Interchange, was the first widely used character set. Standard ASCII uses 7 bits per character, which gives 2 to the power of 7 or 128 different codes. Those cover the upper and lowercase English letters, the digits, punctuation, and a set of control characters such as carriage return and tab. Extended ASCII uses 8 bits, doubling that to 256 codes, adding accented characters and some symbols. 2 facts worth memorizing because they appear constantly. Capital A is 65, and lowercase a is 97, 32 higher, which is not a coincidence, and we will come back to it. Let me show a character actually being stored, because this is the step the whole topic rests on. Take the letter A. First, look it up in the character set. ASCII says A is 65. That is a denary number. Second, convert 65 to binary using the place values from topic 1.1. 128, 64, 32, 16, 8, 4, 2, 1. Does 128 fit into 65? No, so 0. 64? Yes, leaving 1. 32, 16, 8, 4, 2. None of them fit into 1, so zeros. And 1? Yes, leaving nothing. So 65 is 0, 1, 0, 0, 0, 0, 0, 1. Third, that 8-bit pattern is what is physically stored. And now look at what happened. There is no letter anywhere in the computer. There is a binary number and a shared agreement that this particular number should be displayed as the shape A. Now take lowercase a, which is 97. In binary, that is 01100001. Compare the 2 patterns. They are identical except for 1 bit, the 32 column. That is why upper and lowercase differ by exactly 32. The character set was designed so that changing case means flipping a single bit, which is what makes U-case and L-case from topic 8 cheap operations rather than lookups. ASCII has an obvious limitation. 128 or 256 codes cannot begin to cover the world's writing systems. Chinese alone has tens of thousands of characters, and there is no room for Arabic, Greek, Cyrillic, Hindi, or an emoji. Unicode was created to solve exactly that. It uses more bits per character, commonly 16 or 32, which gives it space for over 1 million codes, enough for every writing system in use, historical scripts, mathematical symbols, and emoji, and it was designed with a deliberate compatibility decision worth knowing. The first 128 Unicode codes are identical to ASCII. So A is still 65. That means an ASCII file is already valid Unicode, which is a large part of why the transition was possible at all. Compare the two and the trade-off is clean. Bits per character, ASCII 7 or 8, Unicode 16 or 32. Number of characters, ASCII 128 or 256, Unicode over 1 million. Languages supported, ASCII essentially English only, Unicode effectively all of them. And file size, this is the cost. The same text stored in Unicode takes 2 to 4 times as much space as in ASCII, because every character needs more bits. So the trade is storage for coverage. If a question asks why Unicode is not simply used for everything, that is the answer: larger files and more bandwidth. And if it asks why ASCII is not enough, the answer is that it cannot represent most of the world's languages. Because characters are numbers, you can do arithmetic on them, and 2 consequences appear in exam questions. The first is case conversion. Since upper and lower case differ by exactly 32, Converting a letter to lowercase is adding 32 to its code, and to uppercase is subtracting 32. That is all UCASI and LCASE from topic 8 actually do. The second is sorting. When a computer sorts text, it compares the character codes, not the letters as you think of them. And in ASCII, every capital letter comes before every lowercase letter, because A is 65 and A is 97. So sorting the words banana, apple, and cherry gives apple first, because its capital A has a lower code than either lowercase b or c. That is why a naive sort puts all the capitalized entries above the rest, and why programs that sort names properly convert everything to one case first, before comparing. Notice that both of those follow from the codes being numbers, and neither would make any sense if a character were stored as a shape. 4 things to take into the exam. First, define a character set as an agreed list matching characters to unique binary codes. The words agreed and unique both matter. Second, know the numbers. ASCII is 7 bits giving 128 characters, extended ASCII 8 bits giving 256, Unicode 16 or 32 bits giving over a million. Third, state the trade-off in both directions. Unicode supports far more characters and its files are larger. And fourth, remember that the computer stores a number, not a character. A question asking how a computer represents text wants exactly that idea, that each character is assigned a code which is stored in binary.